Solving separable differential equations. Our objective for today's lesson is to solve separable differential equations by using the separation of variables technique. This is actually something that you've already seen. For day one's lesson, we looked at a word problem in which the instantaneous rate of change of the bacteria population was proportional to the bacteria population. So we had this differential equation that modeled that situation. So let y represent the population of bacteria and let t represent time in hours. I think that was the unit for time. So we had the rate of change of the bacteria population with respect to time was directly proportional to the population of bacteria. And we solved this particular differential equation by using separation of variables. We had 1 over y dy is equal to k dt. We integrated both sides of the equation. You can watch the day one lesson for additional details, but after going through the steps, we got that y was equal to c times e to the kt, and this was, of course, called the general solution of the differential equation. So that was an example in which we took a separable differential equation and we solved it by using the separation of variables technique. And of course, we had to go through a series of steps to get to our general solution. So today we'll look at additional examples for this particular technique. So let's take a look at this problem, solve the separable differential equation. So the differential equation is y prime is equal to 5x divided by y. The first thing that you can do is to recognize that you can write y prime using different notation as dy dx. So dy dx is 5x divided by y, and we're going to now separate the variables. So what does it mean to separate the variables? It means that you're going to get all of the y's with dy and all of the x's with dx. So we're going to multiply both sides of this equation by y. And when we do that, of course, on the right side, y will cancel with y. And then we will multiply both sides of the equation by dx. So when you do that on the left side, the dx will cancel with the dx. And that leaves us with y dy is equal to 5x dx. So that's called the separation of variables step. And after we have successfully separated the variables, the next step is to integrate both sides of the equation. And now we will integrate the left side of the equation by using the power rule for integration. So you need to add 1 to the exponent and divide by the new exponent. And on the right side of the equation, we will also use the power rule for integration. Add 1 to the exponent and divide by the new exponent. And then we have our constant of integration that combines the constant of integration for the left side of the equation and the right side of the equation. When we combine those two constants of integration, we get c sub 1. We just write that on the right side of the equation. So having come this far, what else might we want to do? Maybe we want to clean this up a little bit so we can multiply both sides of the equation by 2. So when we do that, on the left side of the equation, 2 and 2 will cancel, leaving us with y squared. On the right side of the equation, you can distribute the 2 to these two terms, separated by the plus sign. So when you do that, when you multiply the first term by 2, 2 and 2 will cancel, leaving you with 5x squared. And when you multiply the second term by 2, you get 2 times c sub 1. But remember, c sub 1 is just some constant. For example, it could be 20. Well, it could also be 40. It doesn't matter. It's just some constant. So because of that, we don't need to write 2 times c sub 1. We can just write c because c sub 1 is just an arbitrary constant. And if you multiply an arbitrary constant by 2, you just get twice of an arbitrary constant. But you can just say, well, if what I have is twice of 5, why can't I just write c, and c could be 10 or 5, whatever you want it to be. So we write c is equal to 2 times c sub 1, just keeps things simple. And you can actually stop here. This is okay if you want to stop here. Or if you want to go on, you could do the last step that you see here, where I took the positive and the negative square root of y and got y is equal to the positive or the negative square root of 5x squared plus c. Let's take a look at another example. So the instructions are the same. Solve the separable differential equation. Solve the differential equation. So how do we do that? The first thing that we need to do is to just rewrite the y prime using this notation, dy dx. And of course we want to separate the variables, so how do we do that? So let's take a look at how we can do that. You have minus 2xy, so you want to separate the x's and the y's. It's not good that we have a difference of two terms here. That doesn't make it easy for us to separate the x's and the y's. So what we do is we just add 2xy to both sides of the equation. And what happens when we add 2xy to the left side of the equation? Well, negative 2xy plus 2xy will give 0, so you're just left with 1 plus x squared dy dx. But of course, if you add 2xy to the left side of the equation, you have to add 2xy to the right side of the equation as well. So now we're able to separate variables, and here's how we're going to do it. We're going to begin by multiplying both sides of this equation by dx. And when you do that, you get dx and dx will cancel on the left side of the equation, leaving you with 1 plus x squared dy is equal to 2xy dx. So we're just taking our first step to separate the variables. Now we see that the variables have not been separated, but we're making progress. So what do we still need to do? Well, you've got dy here, so you want all of the y's to be on the left side of the equation. You've got dx here, so you want all of the x's to be on the right side of the equation. So that's going to be what we'll try to do. So on the right side of the equation, currently we see a y. We don't want that there. So we multiply both sides of the equation by 1 over y. And then when you do that, the y and the 1 over y will cancel on the right side of the equation, leaving 2x dx, which is good. But you still have the 1 plus x squared on the left side of the equation. You don't want it there. So what are we going to do? You're going to multiply both sides of the equation by 1 over 1 plus x squared. So when you do that to both sides of the equation, on the left side of the equation, it will cancel with the 1 plus x squared, leaving you with just 1 over y dy. And on the right side of the equation, you'll have 2x times 1 over 1 plus x squared, which is 2x over 1 plus x squared times dx. So now the variables have been separated. We have all of the y's with dy and all of the x's with dx. This is called the separation of variables step. You've got to get that right to get the rest of the problem correct. So what do we do next? We should integrate both sides of the equation, and that's what you see here. We integrate both sides of the equation. And you may remember the log rule for integration. So the left side, the indefinite integral is just natural log of the absolute value of y. And on the right side of the equation, you may not see it, so you may have to do what we call integration by substitution. Let u be equal to the denominator. Again, you may not see it right away, but it works out really nicely, as you can see from my work over here. Let u be equal to 1 plus x squared. Then the differential of u du will be the derivative of 1 plus x squared, which is 2x. So you have 2x dx. And then you're going to change variables. So what do? You use your substitution to change variables. So the 1 plus x squared becomes u, and the 2x dx becomes du. And of course, the 1 plus x squared is in the denominator, so you have 1 over u. So now you have successfully changed variables, and this looks like something that we can apply the log rule for. Here's the log rule for integration, and we have the natural log of the absolute value of u plus some constant. We'll call it c sub 1 for now. And finally, replace u with what u represents. U is equal to 1 plus x squared. So we have the natural log of the absolute value of 1 plus x squared plus c sub 1. And that's what we write here. So what we want to do now is to maybe clean this up a little bit. Now, one thing that you'll notice is that we have a constant here, c sub 1. It's an arbitrary constant. Natural log of a constant is also just a constant. So I can just write natural log of some constant c is equal to c sub 1. Because natural log just means e raised to a power to get c. So natural log of c is the power to which e must be raised to get the constant c, and e has to be raised to some value to get that. So if the constant here is c, then you're just raising e to some arbitrary constant c sub 1 to get the arbitrary constant c. So you can rewrite c sub 1 as natural log of c. Now, if you don't do this, it's okay. This is an acceptable form for the answer, but if you wanted to try to get y by itself, then you would do what we're just talking about now. So look at how we progress with trying to isolate y. So the next step is to use a property of logarithms. You have a sum of two logarithms with the same base, so you can use something called the product property of logarithms and condense this expression as the natural log of c times 1 plus x squared. Finally, if you want to get y by itself, you can exponentiate both sides of the equation with the base e. And when you do that, you get y by itself on the left side, and on the right side of the equation, you'll have c times 1 plus x squared. Now, as long as you have natural log, the argument has to be positive. So that's why you have the absolute value for y here. And 1 plus x squared is always going to be positive. So c would have to be positive. But you do have the absolute value of y here. So it's possible that y could be negative, but you're forcing it to be positive by taking the absolute value. So when you take the exponentiation of both sides of the equation, when you exponentiate both sides of the equation with base e to isolate y, there is the possibility that y could be negative. So how do you deal with that? Well, on the right side, you just have c times 1 plus x squared. And remember, c is an arbitrary constant. So to make y negative, you can just choose c in an appropriate way to make y positive or negative. But like I said earlier, if you wanted to stop here, that's okay. If you wanted to continue, any of these steps would also be okay, or anything that's equivalent to each of those steps would be okay as your answer. So today we looked at separable differential equations and how to solve them. We solve them by using something called the separation of variables technique. Again, this is not new because you'd already seen this with the day 1 lesson where we had an instantaneous rate of change that was proportional to the quantity that we had. So the rate of change of a particular quantity was proportional to the quantity itself, and we solved that differential equation by using separation of variables, and of course there were some steps in between, and this was the general solution. And what we did today was solving separable differential equations by separating variables. So that's how the two problems that you saw in today's lesson relate to a part of what you saw for the day 1 lesson.